3-dimensional space, you need 3. If you have 17-dimensional space, how many vectors do we need? We need 17. Okay. I know that you have not done that all this depth, very high dimensional space, but this is something that I want you to perceive from the first weeks. If you have 6-dimensional space, you need 6 different vectors to describe any point in there. Okay, but these have to be linearly independent. For example, any 2 points on this whiteboard, we need 2 vectors, which x and y. This would be enough. Okay. Now x and y don't have to be orthogonal, don't have to be 90 degrees. We can also use this other 2 sets. We can have this x1, and this can be x2. These 2 are also another pair of coordinates with which we can represent any point on the board. But let's go back to Cartesian coordinate system. What is Cartesian coordinate system? It is orthogonal. We have x and y at 90 degrees. Then we can ask the following question. Can we describe this point as a function of x and y? Yes. I mean, we just project this one, how when this projects onto, it projects here. Then we project this one also here. We get this. And how do we do the projection? I mean, how can we find the projection of...
These are quadrants. So
These
are the quadrants.
That's true. These are the 4 quadrants of the Cartesian coordinate system. But let's go back actually to projection. You know, you learned last week what the projection was. Do you remember? So how do we find the projection of any point here given 2 numbers?
2 and 3.
2 and 3. So what is the projection of 2 and 3 in the Cartesian coordinate system? How do we find it? We do the inner product of 2, 3. We take the inner product with the unit vector along the axis of interest. What is the unit vector along the x? 1, 0, right? This is the projection. What else? The projection along the y is 2, 3, inner product with 0, 1, right? Okay, we get this one. Now let me ask you this other question. What is the projection of vector A, which can be equal to 1, 4? Let me call it like this: projection of A along vector B, which can be -1, 3. How can we find this? How do we find the projection?
By inner product?
That's true.
But
it is true. This is the only thing that you need to do. But it's not inner product with this one. We have to take the inner product with the unit vector u, which is along the vector b. Okay. So what is the unit vector u along the direction of b? This is defined as, how did we do this last time?
B over magnitude.
That's true. That's true. Thank you for over the magnitude of b. So in this case, this would be equal to whatever b is. What is the magnitude of b?
Square root of inner product.
That is true. So this is equal to the square root of
-1, 3 and -1, 2.
That is correct. So let's move fast here. So then we get -1. What is this? Root 10. That is true. Root 10. So then here we get a unit vector along the direction of b. This is 1 over the root 10 of -1, 3.
-1 root of 10.
Yes, or this is also equal -1 over root 10, 3 over root 10. Now we can solve it. So what is the projection of A along b -1, 3? And by the way, what does this correspond to? 1, 4 is like 1, 2, 3, 4. So 1, 4 is going to be a vector like this. This is vector A. And b is -1, 3. -1 is right here, 1, 2, 3. So this look is this vector. So when we say what is the projection of A onto this direction, right? How do we find the projection? We just multiply this A with the cosine of this angle, right? So we're kind of expecting to get a value which is like this. So the rest is, so what we need to do, the projection of A along this direction, the answer is the following. This is the inner product of A with UB. And let's not forget of finding this unit vector here, because also, this 1, 0, this is the unit vector along the x-axis. This is the unit vector along the y-axis. So if we are in two-dimensional space, we are going to get unit vectors that look like this. Okay? If we are dealing with three-dimensional space, the most common unit vectors, they will look like this, 0, 1, 0, and we get 0, 0, 1. So often, we refer to this one as x-axis, this would be the y-axis, and this, we consider the third orthogonal coordinate system, z-axis. So then, we just move ahead here fast. So here we do the inner product, A, with this A transpose, this is 1, 4, and then we multiply here with minus 1 over square root of 10, 3 over square root of 10. Then the projection of these two is going to be 1 minus 1 over square root of 10 plus 12 over square root of 10. So we get here 11 over square root of 10. We can multiply both sides with square root of 10. So we can write this one 11 over 10 times square root of 10. Either answer is okay. I mean, you don't need to multiply this one, but it might look a little more elegant. So this is what we tried, what we can use to find the projection of certain vectors along some other directions. Now, this is very important. This is very important because it is sometimes very straightforward to find the projection of this one onto this, because it's going to be 2. Okay, the projection of this onto this one is going to be 3. Why did I say here 0? Because the projection of this one along the y-axis is 3. This is straightforward. It's more generalized. So I just want you to remember this one a little more. Okay. So if you have a point in three-dimensional space, point P is equal to minus 1, 2, 3. What is the projection of point P along the z-axis?
Minus 1.
Z-axis. 3. Okay, that's true. How do we find it? We multiply this one with unit vector along the z-axis. But if we ask about some, what is the projection of this one along some other direction, we know how to do it because we do it something like this. We will do the projection of vector spaces a lot during this class, but let's continue.
Can we make just a piece so we copy the one?
Yes, yes. Meanwhile, I can write a few words. Well, we can take a picture, we have it on record, but we'll issue it. And by the way, I just want you to remind also regarding something else. So we're going to talk about the planes, but let's imagine also for again a line. It is always a line and can be represented like this. Okay, a line, it doesn't have to be always in two-dimensional space. A line, it can be represented something. I'm just throwing out some numbers. Let's say line L1. It is equivalent, or it can be equal to 1, 2 plus t times minus 1, 4. What does this mean? We have a slope like this. We multiply the slope with any number t, which is from minus infinity to infinity. It's real number space, plus some reference point.
So we get a line.
That is true. But then we can also have another line, which can be defined as 1, 0, minus 3 plus t, or let's call this one s, another parameter. This is also a real number, times another direction, minus 1, 1. This is still a line, but this is a line in three-dimensional space. So if we have three-dimensional space, which can be defined as x-axis is like this, y-axis is along this wall, and z-axis is moving like this. We can define a line which moves along this axis, probably by this equation, which is like this. But it will be a line in three-dimensional space. This is a line in two-dimensional space. So if you put a line on the whiteboard, we do this.
When we find the inner value over there, a and unit vector b,
Yes.
I was supposed to find the square root of 1, 4, and then 1, 4 again, plus square root of vectors unit b, and
Okay.
1 minus 1 square root of 10. I mean, you just multiply them.
I believe we just multiply them.
Yeah. Aren't we supposed to find the inner value like we did when we found the magnitude of
Oh, but this is the magnitude. I mean, this is the magnitude of one vector, and the magnitude is always, so the inner product B and B is this. But magnitude is the square root of something. Here, we don't need to take the square root. Okay?
Square root is only used when we find the magnitude.
Yes, that's true. Yes. And maybe it's good to also, so let's have a look. What is B? Or give me one B here. So this is minus 1, 3. Minus 1, 3 is this vector. Okay. And by the way, let's forget about the inner product and magnitude we learned here. How do you find the length of this vector B? And the length, it means magnitude, right? It's how long it is. It's not the direction. So forget what we did this last week together.
We take example.
Let's use Pythagorean theorem. How do you find it?
We take our coordinates.
Yes, magnitude of B would be equal to the square root of 3 squared plus 1 squared, right? What do we get?
That's that.
Square root 10. Yeah, root 10. This is the magnitude of B. Similarly, I mean, we get the same result here, right? So it's like applying the Pythagorean theorem, but in a generalized form. Okay. Yeah. Now, this was line in 2D and 3D. Now, let's move a little planes. So planes, they can be described as any point x, which is equal to some reference point b, plus some vector b, and plus some vector w. This is the equation of a plane. So this is the equation of a plane, and before we discuss the general expression of the plane, let's see an example. Let's assume that we have one line, L1, which is equal to 1, 3, 4, plus a slope, which is 1, 2, minus 1. Here, this was one line. This is another line, and this line, we denote this one as 5, 6, 1, 5, 6, 1, plus p, minus 2. On let's say this one S, just so that we don't get confused, minus 2, 1, 7. Okay, so here we have two lines, and then the first question that we may look for is the following. Can these two lines be parallel to each other? Can we perceive it? Because, so what is the definition? I remember when I was in 7th grade, professor asked us, when are two lines parallel? He gave a lot of definitions. And one friend in my class, his name was Elkid, and he found it. So two lines, for example, here's the definition of two lines that are parallel. Where are the lines that it's not enough?
Lines that go along the same direction, but
Same plane? Yeah, that's true. So two lines that are in the same plane and don't intersect, these are considered parallel. Okay. So Elkid was in my class in 7th grade. He said, okay, there's the Greek mathematician said, okay, so you have to find it, he got it, right? So one line, for example, let's say that line which is going at the intersection of the ceiling with this vertical wall, that's one line. And then you have another line which is going down here with the floor and this wall. These two lines are not parallel. That's Q. Okay, so they are not parallel. So they are parallel only when they are on the same plane. So that just to remind ourselves, if we were on two-dimensional plane, everything is good because you don't have to do too much tricks. But now let's have a look at these two lines, and the question is that can they be parallel or do they ever intersect? How can you check this? So
Should we check the, I think after T or C? So
Yes.
should that be like equal or
well, we can try to do this one. We can say 1 plus t, so we can check if this is ever equal to 5 minus 2s. 5 minus 2s. We have two unknowns, we need two equations, right? And then we can also do this one, 3 plus 2t. This would be equal to 6 plus s. 6 plus s. Now, can we find a solution for this system of equation? What can you say? Let's find this together. So here, t is equal to 4 minus 2s. We can insert this one here, but by the way, this is 3. So this is what we get. So then here we have 2t. This 3, we pass it to the other side. This is 3 plus s. This t, we substitute it in here. We get 2 times 4 minus 2s. I need some help here. This is 3 plus s. So here we get 8 minus 4s. This is equal to 3 plus s. Then we can simplify this a little further. This would be equal to, what is this? 5, right?
S is equal to 1.
5 is equal to, yeah. Well, what is this? 5s?
5s.
Okay. But then, can you think about this? So s is equal to 1. Okay.
But we can also do 3.
Yes, but we have two unknowns, and then we can try that one. And so apparently we can. But the question is, if we insert here s equal to 1, I might, doing this kind of calculations, you can also try this at home. You try and solve another relation. Let me think for a moment. So apparently we can find an s which is 1, and t would then be equal to 2. T would be equal to 2. Okay.
we should
So-
like prove it with the last one, for example, 4 plus minus T.
Let's try it. Okay. 4 minus t. This is
1
equal
plus
to
7s.
1 plus 7s. Let's substitute these values and let's see. I mean, if the two intersect, this should end up being equal. No, I mean, this identity should be true. So right now we are questioning this identity. Then we have here 4
Minus 2.
minus 2. This is equal 1
7.
plus 7s. What is 7s? 7. So this is equal to 2. This is equal to 8. So apparently it's not true. So this means that these two lines, apparently, they never intersect. Okay? We cannot find S and T such that the same point will be both in L1 and L2. And two lines, they either have one intersection, one common point. And actually this is something which is very, very fundamental. If you have two lines, how many intersection points they might have? One. Is there any other option?
Or they could be the same. Or, yeah.
Infinite number of intersections, okay,
Or 0.
or 0. That's true. So actually, often in linear algebra, we will often be faced with the options of having no intersection, okay, one intersection and an infinite number of intersections. So this one, we'll see this a lot of times, but then we'll use a different language it will more have to do something with finding the solutions of systems. Whenever we try to solve equations, these equations can have no solution, can have an infinite number of solutions, or no solution at all. So no, or only one. They can have no solution, infinite number of solutions, or a single one, which we call it unique solution. Now, L1 and L2, apparently they don't intersect. Okay. Let's bring another line. Let's assume we have a line L3, which is equal to 5, 6, minus 5, plus P, minus 2, 1, 7. So now we have to check actually whether this line intersects with either one of these. If we do a same system of equation for L1 and L3, we may find out, maybe you can work this one at home, you may find out that L1 and L3, they do intersect. L1. Can you see it right away? And L1 Oh, okay, maybe, but you need to, I believe all of us need to do this kind of calculations and to confirm it as we try to do it, but we ended up having no intersection because this identity was not confirmed. But then L1 and L3, if you do a similar check, they do intersect. At a single point, which is 3, 7, 2. How they intersect at 3, 7, 2? Using different values of t's there and t here. Now, the thing is that if L1 and L3 intersect, what they do is that if they intersect, they
With
define a plane.
T2, they intersected with T's value is 2.
They do? Okay.
Yeah, if T value is 2 and the same, it comes to the same result, 3, 7, 2. For L1.
Okay, so that's okay. We can say that whenever t equal to 2, and let's write this one s, okay, right? Just so that we don't get confused. What could be s? We can also find this out. What could be s? S can be 1 maybe?
Yeah, 1.
Yeah, 1.
Yeah, 1, S1, T2 and S1 gives intersection.
We find the intersection between L1 and L3. Okay, that is true. Now, if two lines intersect, with these two lines, let's not forget that a single line, it has one direction. The other line, it corresponds to a different direction. That means that it would correspond to these different, one would be the V, and the other one would be the W. Okay, so then in this case, we can say that if we define a plane, the equation of the plane P, this would correspond to being 3 points x, y, z, and this would be equal to this point of reference, 3, 7, 2, or just for a moment, we can assume that we don't know this P, okay? Let's keep this as a question mark. We don't know this yet. Plus s times. Now, if we are dealing with 1 and 3, we can say that this is 1, 2 minus 1 plus p minus 2, 1, 7. Minus 2, 1, 7. Because why? Because this would be equivalent to this point p plus, we call it this one s, p plus p w. We don't know these values yet, but what we can do is the following. We can use this point of intersection as a reference, because we can set here S0 and T0, and then whenever these two are equal to 0, that means that we should have an equality for both sides, and then so this would be the definition of the equation of a specific plane. So let's see another example. So let's assume, and by the way, let me ask you one question. Does this plane pass through the origin? what can you say? Well, the first choice is the following. We can equal this one to the origin, which has to be looking like this. You can try this one. You can try to solve this equation, and you may provide the answer to me on Friday. Okay. So find whether plane passes to the origin of the Cartesian coordinate system, which in this case is going to be the xyz 3D. Now let's see another example. Let's consider that we have a plane given a plane, and this plane it is defined as x, y, z. But this would be equal to s times 1, 2, minus 1 plus t times minus 2, 1, 7. So presumably this is equal to sv plus t w. So this is a plane. Now, one question that we can come up with is the following. Let's find Cartesian equation, Cartesian equation representation of the plane. That's the question, okay? If you remember, in the previous hour, we did lines on space, and then what would be the equation of a line? The equation of a line, it looks something like this. Y was equal to the slope mx plus b. Okay? Now, the equation of a plane, it should look something like this. Ax plus by plus cz, this would be equal to b, some value. Okay? So we should have all the three equations on the three-dimensional space in an equation which is going to look something like this. If we use parameters, what we do in parameter, and the limit vector, so the general expression is going to look something like this. Now, if this is the general expression, which we wrote it also here, what is different in this expression? P is what? Is 0, right? P is 0. So apparently, and then if I ask you the same question that similar to this problem that you're going to do it at home, as a homework, this plane which is given here, do you think that this plane can pass through the origin?
Yes.
How?
S and T are close to 0.
That's true. That is correct. Okay, that's true. So yes, this can pass through the origin. It is very explicit. It is obvious. So now, how can we transform this presentation into something like this presentation? All we need to do is that we need to eliminate S and T. Okay? How can we eliminate S and T? First of all, we see that x is equal to s minus 2t, y is equal to 2s plus t, and then s, from the first expression, we can use different tricks, but it can be faster than me most of the time. So here s would be equal to x plus 2t. And then we substitute this s here, and we get y is equal to 2 times s, which is x plus 2t plus t. So y it is equal to 2x plus 5t. This is y. Then from here, we can define t as a function of x and y, and t would be equal to 1/5 of y minus 2x. Y minus 2x. Then we just need, so we use these two equations. This is all the information we received. We can also use the last equation, which is z is equal to minus s plus 7t. Now, in this expression, this s, we can write this one as a function of x and t, right? and t, we can substitute here as a function of x and y. So it looks like now, if we substitute everything, let me use this space here. So z would be equal to minus s. Minus s, it is minus x minus 2t. T, let me substitute t right away, which is 1/5 y minus 2x. This was minus s plus 7t. Plus 7t, t is equal to 1/5 of y minus 2x. And then we continue again. Huh? Let me check. No, this is y minus 2x. Okay, that looks, it is correct. Z is equal to minus x minus 2y over 5 plus 4 over 5x plus 7 over 5y minus 14 over 5x. So this is the z. What can help us is that we can multiply everything by 5 and see if things can get simpler. So we can get here 5z. This would be minus 5x. This is gone, this is gone. Simplify, simplify. And then let's see, we can bring together the x's. So this is here 5z. This would be equal to minus 5x plus 4 minus x minus 14 minus 15x. The y, it is, what is it? Is it 5? Yeah. So we can cancel out, apparently, the z. We can divide by 5 everywhere. And we can obtain the following. We can get 3x minus y plus z. This is equal to 0. Okay, so this looks like the final equation of this plane. One thing that we can report in this class is that the equations of the let me ask you something. Can you calculate what is the cross product between this direction and this direction? Let's find it. Anyone remembers the cross product? How we find the, when we multiply two vectors with each other? We're going to learn, of course, a lot of things. So let's look for a moment cross product of two vectors A, B, this is equal to C. So these vectors here, let's consider this 1, 2, minus 1. One, 2, minus 1, minus 2, 1, 7, minus 2, 1, 7. This would be equal to I. You know, you remember the determinant of a small maze is 2 by 2? What was it? The diagonals? Yeah, the difference of two diagonals, right? So this I, what is the determinant of this one? I times 2 times 7 minus 1 is 1. So this becomes 2 times 7, 14, 15. Minus j. And this minus j is equal to now, we have this other matrix, which is going to be 1 times 7 minus this other trick. So this is going to be 1 times 7 minus 2. What do we get? 5. Plus k. What is k? K, it is the direction along the z-axis, and what do we get here? 1 times 1, 1, minus 4, plus 4, 5. Okay, we get here 5. So what did we get here? We had a vector A, so vector A, it was equal to 1, 2, minus 1. Vector B, it was equal to minus 2, 1, 1, 7. What do these two correspond to? The two correspond to these two directions, right? And these two directions, we calculated the cross product. the cross product of two vectors gives a third vector, which in this case is going to be, let's call this one vector C, which is equal to, can you help me here? This is 15 minus 5 and 5. Now, this vector, we can consider this one as equivalent, or because they have the same direction, it's not equal, equivalent. Divide by 5, we get 3 minus 1, 1. Now, can you have a look at this vector and compare it with the coefficients in front of the plane equation? They are the same. So now, what we can say is that this is the equation of the plane using the Cartesian representation. And these coefficients that we see here, they determine a vector which is perpendicular to the plane. Okay? So what we can say here is that, in fact, the equation of the plane in a Cartesian coordinate system, it can be represented like this. The inner product of any vector n, normal vector, with x, this is equal to 0. Okay? But you know what is the inner product, right? The inner product is what? This is the direction perpendicular to the plane. And by the way, this is one direction, this is another one, which can be something like this, right? Of course, they intersect at one point. We made sure about that. You can double check this at home. Now, if you take the cross product between these two vectors, we get this. We get another vector that is perpendicular to both, which is perpendicular to the direction of the plane. So now, we use the cross product. We found this vector. Apparently, it ended up to being what it was in our equation. So now, this is the normal vector. This n, what is the normal vector? It is 3 minus 1, 1. So if we take the inner product, 3 minus 1, 1, and this is a matrix which is 1 by 3, right? I mean, you know, it's much, we're specialists in this. And the vector x, it corresponds x, y, z, okay? This is another vector which is 3 by 1. 1 by 3. If we multiply the vector which is 3 by 1, what do we get? We get a scalar, right? There's just some numbers. It's like, so then this is equal to, we get 3x minus y plus z, right? And this is also equal to 0, but in principle, it looks like we had an equation of a plane which looks like this, represented like this. We can write it in a Cartesian coordinate representation, which will end up into being like this. But we prefer in this course to elegantly write these like this. Okay? Now, your homework, it will be also this one. Try to find the Cartesian representation of this equation for this plane. Okay? There is this plane, let's call this one plane P2, and find bring this Friday, okay? You have 2 days to work out with these. You don't have too much homeworks at this stage of your semester. You have 1 hour driving home to Gabriel in New York, Chardonnay, na autobus. E do outro professor,
Aqui?
calma, não pensa, professor. Puxei para din hasen. Tem ninguém para din hasen?